There are two ways that you can accomplish Syn dihydroxylation. We saw how a hydroxyl group is an OH. If you add two OHs, then it's dihydroxylation, and if you add them on the same side of a double bond, then it's Syn dihydroxylation. So you'll notice you're adding an OH and they're both pointing out at you, but they could also both be pointing away from you in these examples. Now, there are two recipes because they both have advantages and disadvantages. So one is using a molecule called osmium tetroxide. That's going to stick the two oxygens onto the molecule, and then you kick the osmium off, you replace it with hydrogens in this second step. The second one involves a molecule called potassium permanganate, and crucially, you have to keep that cold and basic, so sodium hydroxide, in order to prevent side reactions from happening. Okay, well, let's look at the similarities first, and we'll look at that by seeing the similar structures of osmium tetroxide and potassium permanganate. In both cases, you have a transition metal. In osmium tetroxide, that's osmium. In potassium permanganate, that's manganese. So here we're doing osmium tetroxide and potassium permanganate. Okay, so what we're noticing first is that we have this transition metal in each case, and then we have the four oxygens bonded to it, and the structure is really similar in each of these cases. Now these are transition metals. They're in they have d orbitals, and so they can hold more than 8 valence electrons. So you can see the similarity in the structure of osmium tetroxide and potassium permanganate. So this is the permanganate ion all by itself. You'll see one of the oxygens is single bonded to the manganese and has a negative charge, and that's why you have this potassium there. The potassium is a counter ion to stabilize that one oxygen in permanganate. Okay, well, one interesting fact, first just a sort of trivia thing, osmium is one of the densest elements on the periodic table. It weighs around 23 grams per milliliter. A milliliter is about the size of the end of your pinky. And that means that that's around 23 times heavier than, or more dense than water. So if you think about the weight of a gallon of water, if you had a gallon of osmium metal, that'd be around 23 times heavier. Now when you react it with oxygen, it forms this osmium tetroxide, and that is really good at forming these cis diols, or it's really good at forming this Syn dihydroxylation. So good, in fact, that it's extremely toxic. Osmium itself is pretty toxic, and it's like an almost bluish silver metal. When you react it with the oxygen, it turns into a sort of translucent, light pale yellow solid liquid that evaporates really easily. So you could imagine that if you take that and that evaporates and it gets in your eyes, in the back of your eyes, in order to see, you have this molecule here, which is called retinol. You can see how many pi bonds, how many alkenes you have there. Imagine osmium tetroxide evaporating and then liquefying into your eyes and then reacting with every single one of these. It would completely destroy and react with that molecule. And so it's really toxic, so you're unlikely to work with it in an undergraduate laboratory. And when you work with it in either a graduate laboratory or research laboratory, they try to use very small amounts of it, and it's in a very controlled situation because it's so toxic. Apparently, if it does get in your eyes, it takes a few months, and there's a chance that you'll get your eyesight back, but it could make you blind forever. So osmium tetroxide is kind of a nasty thing, both for people and for the environment, which is why there is this alternative of potassium permanganate. Potassium permanganate is not as toxic. It's often used in undergraduate laboratories, even in general chemistry. It's a sort of purplish, dark purple liquid often. And you get it on your finger and it stains your, or you get it on your, it'd be unfortunate if you spilled it on yourself. You should be using gloves, but if you get it on your skin, it'll stain your skin for a few weeks. You'll have little splotches of where it got on you, which those eventually go away. So it's toxic, but not as toxic as osmium tetroxide. So that's why you have these two options. Osmium tetroxide, which does an amazing job, but is toxic. Osmium tetroxide not only is really good at doing this, with reacting with alkenes, but it's really good about being selective. It doesn't react with other features of molecules, other functional groups that we'll learn about in organic chemistry too. Potassium permanganate is much safer, but it will react with everything, and it's really just like a bag of piranhas. Like putting in potassium permanganate with the molecules, like throwing in a bag of piranhas. It just reacts and chews off everything in your molecule, so you have to be really careful to see if your molecule can withstand potassium permanganate. Okay, so in terms of the mechanism is going to be really similar for both of these. If you have an alkene, so that pi bond there, two of the oxygen sort of lands on the face of that at the same time, and that's responsible for the Syn addition. So one of these, this pi bond, remember osmium and manganese are metals. In general, when you have a metal, you want to think very low electronegativity. This has these oxygens all repelling each other, so it's hard for the osmium to keep hold of all of those electrons. It's a metal and has very low electronegativity. So some of these metals are going to leak out. They're reactive, and they end up working in a sort of circular fashion. One of these pi bonds attacks this carbon, that pushes these electrons away to attack this osmium, and those electrons go onto the osmium itself. And so you form what's called an osmate, a cyclic osmate ester. So you have oxygen single bonded to the osmium, a new lone pair on the osmium, and then your other two oxygens there. So that's what you form, and these are the two oxygens in the diol. You can see why they are adding Syn, because they're adding on the same face through the same molecule. Those two oxygens are the two oxygens that you get in the diol. It doesn't take too much to replace this osmium with just hydrogens. All you need is water, and sometimes this is catalyzed by sodium bisulfate or sodium sulfite, sodium bisulfite or sodium sulfite. So you'd have sodium bisulfite, looks like that, and that would look like this. That can contribute a hydrogen. So you have these lone pairs in this oxygen that can contribute a hydrogen to that osmate ester. You can see this is an acidic hydrogen because this lone pair is going to be stabilized through resonance with that allylic. It's allylic to that pi bond. So that will form this. This oxygen now has a full positive charge, and then water can come in. As a nucleophile, the oxygen in water is slightly negative. The osmium is a metal, so it has low electronegativity. It's slightly positive here, especially bonded to those really electronegative oxygens. And the water can attack the osmium and effectively kick off this good leaving group that we made. So we have one of our diols, and then that process just happens again. You get another proton transfer from another sodium bisulfite. This other oxygen steals one of those slightly positive hydrogens to turn itself into sort of a better leaving group. Has a full positive charge, and then you just need another water molecule to come in. Slightly negative oxygen attacks the slightly positive osmium and kicks that off. So you end up with your diol. And the two oxygens will be syn, so for example, they'll either both be coming out or both be going away because they added on the same face through the osmium tetroxide. Now, here, the way I have this, I have two waters attached. Those end up undergoing, these oxygens with the positive charges, those end up undergoing two separate proton transfers that I won't draw out here because it wouldn't add so much to our understanding, but you could see how a water could come by, steal one of these hydrogens, and the electrons could come on, snap back onto the oxygen there and stabilize the positive charge. So after a couple proton transfers, this is what you would get. Oops, with this osmium here. That's what you'd get. Crucially, you'd have the Syn diol, and then the osmium tetroxide will have been turned into, two of the double bonds to the oxygens will have been turned into single bonds to OHs. Now, that means that you're using, if you do this just with osmium tetroxide, then you are using up the osmium tetroxide, and so you have to use a lot of this toxic compound. So instead of doing that, people want to reduce the amount of osmium tetroxide you're using because it's so toxic, that instead of just using this in bulk, they'll use it as a catalyst. They'll regenerate it. They'll turn this back into its former self. Osmium with 4 double bonds to oxygen that can go through the same reaction all over again by using an oxidizing agent. And this can be different things. One common one is peroxide. So, for example, you could use peroxide with a tert-butyl group, like this, or any other peroxide, ROOR. And another one is one called NMO. Now, NMO looks a little bit like this. And it ends up acting as an oxidizing agent, contributing this oxygen, using that oxygen to reform second bonds to these oxygens here. And the NMO stands for N-methylmorpholine N. N-oxide. So NMO. You don't need to know the structure for that or the name for that, but what you should know, just as a sort of background piece of information, is that these other things, through a mechanism that's maybe long and complicated and a little far afield for us, those reagents are turning this osmium compound that got used up back into its original self. They let you use osmium tetroxide as a catalyst rather than as a reagent. So you only need a tiny amount of it, and that helps to make it safer for the person doing the reaction and also more environmentally friendly. You could see how you could go through that same exact mechanism with potassium permanganate. The features are the same. You'd have this feature here is the same as this feature here. You just have manganese instead of osmium. And so you could go through a similar reaction. The sodium hydroxide here and the cold temperature is helping to prevent other reactions from happening. Potassium permanganate is very reactive, and so you have to prevent side reactions from happening. That's what the cold temperature and the base are there for. The other mechanistic details are kind of far afield from us, but hopefully you can see, just seeing the structures of these, you can see why it's syn addition. These two oxygens will be adding on the same face of the double bond because they're pointing in the same direction in the osmium tetroxide or in the permanganate ion. And hopefully now you also at least have a sense of why there are two recipes here. You have a really efficient but very toxic recipe, and you have a less toxic recipe but with side reactions and less efficient. And you have some sense of what these other reagents are doing. So this adds the two oxygens on. This other thing replaces the osmium with hydrogens. This adds the two oxygens on, and then the other things are preventing the side reactions from happening. So those are just a few concepts that's good to know for Syn dihydroxylation.